have been listening to Professor Arvind lecture about the probability space in the basic setting in which concepts of probability are used and written down, etc. I am sure you will agree with me from the lectures. You can see that the experiment plays a critical role. Now, in this lecture I am going to give you examples of say 4 or 5 very simple experiments, and then I will go on to describe them in some detail, and these examples we will carry over throughout the course. So, we will have it coming week after week for you to know. So, I think these examples are very critical and they will help you solve so many problems. So, let me get started. So, the first experiment that we will consider is toss a coin. Okay. Many of us know what this experiment is. There is a coin, it has 2 sides, one side is heads, the other side is tails. Okay. And we are going to toss it up. We do not know which side is going to come up on top. Okay. And if heads comes on top, you say heads is the result, and if tails comes on top we say tails is the result. It is a very simple experiment. It has only 2 outcomes. The first outcome the first outcome is heads, the second outcome is tails. Okay. So, hopefully this experiment is clear to you. I will have much more to say about this experiment as we go along, but for now this is just the first week. So, I am only describing the experiment in this video. So, we will just accept this experiment. It is a very simple experiment, hopefully it is clear to you. Okay. The second experiment that we will be using quite often in examples is throw a die. Okay. So, when I say a die, I mean a 6-faced die. Okay. So, it is a small cube, you must have seen this. On each face of the cube some number is marked, I mean some small dots are made to mark numbers, and the numbers are 6-faced die. Each face is numbered from 1 to 6. Okay. And when you throw it, you do not know which side is going to come up on top. So, that is the outcome of the experiment. So, the outcome is one of 6 possibilities. It could be 1, it could be 2, it could be 3, it could be 4, it could be 5, it could be 6. So, this is the second experiment that we will use often in our examples. So, the first experiment is tossing a coin. It has 2 outcomes, heads or tails. Second experiment is throwing a die. It is a 6-faced die. Each face is numbered from 1 to 6, and there are 6 outcomes that are possible. So, these outcomes are random. Hopefully, you agree that is true. Okay. The third experiment is draw a card from a pack. Okay. I want to say a few more things about these cards and the pack of cards, what kind of cards does it have, etc., etc., so that we know clearly what we are talking about. So, what is a pack of cards? Pack of 52 cards. Okay. There are 4 suits. What are the suits called? Spades, clubs. These are the 2 black suits, spades. I am going to try and draw a picture here. This is going to be an ugly picture. So, that is the spades, and then clubs, it is clubs, and then we have the red suits. These 2 are black, right, and then you have the red suits which are hearts and diamonds. Now, maybe I should use the red color to show the hearts and diamond. Okay. So, these are the 4 suits in the pack of cards. There are 13 cards in each suit. Okay. What are the 13 cards? We will start with 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have the jack, the queen, the king, and the ace. So, what are these things? I should write it out. It is called the jack, queen, king, and the ace. Okay. So, these are the 13 cards in each suit. I am not going to try and draw the jack and the queen and the king for you, it will be really too ugly if I draw it. Hopefully, you have seen a pack of cards before, that is how it looks. Okay. So, I need some sort of notation to describe the outcomes. So, if I have a pack of cards and I shuffle it a lot, mix things up so that I do not know what I am going to draw, and then I draw a card from the pack at random. The card could be any one of the 52 cards, it could be any one of the 4 suits, it could be any one of the 4 letters that are written to represent the card. It could be any one of the 13 things out there from 2 to A. It could be 2, 3, 4 or 10 up to 10 or J or Q or K or Ace. Okay. So, the outcome is 52 possibilities. How does that work? It could be 2 spades, 3 spades, 4 spades all the way till ace of spades, or it could be 2 clubs, 3 clubs, 4 clubs all the way till ace of clubs, or it could be 2 hearts, 3 hearts, 4 hearts all the way till ace of heart, or it could be 2 diamond, 3 diamond, 4 diamond all the way till ace of diamond. So, there are 52 outcomes. This is how it works. Is that okay? So, you see what I'm doing when I talk about these experiments. I'm describing the experiment, I'm describing the outcomes, not just describing, I'm also denoting the outcomes, introducing some notation for the outcomes and putting it together in some sort of a set, okay, set of all possible outcomes I'm collecting together. So, this is also equally important. I mean, quite often we do probability without really having a notation for the set of outcomes. Maybe if you are really experienced, you can go to that, but when you start out, it is always good to have some notation for the list of all possible outcomes. In some cases, the list of all possible outcomes is easy to write down. In some cases, it can be very long or confusing. So, the next 2 examples we are going to see maybe are a little bit more confusing than the current examples, but they are equally important as well. Okay. The next example we will see is draw a ball from an urn. Okay. By the way, what is an urn? Urn is like a pot. Okay. It's a pot. So, maybe I should draw a pot. Okay. So, you have a pot here. This is my urn, and inside the urn there are, let us say, several balls of different colors. Okay. So, that is the main assumption in these kind of experiments. You have, let us say, black colored balls lying somewhere. Okay. So, I am letting the balls fly in the air. So, they are not going to fly, they will be lying somewhere. You could have blue colored balls. Okay. Somebody must have put all these balls inside this urn at some point in time. So, they would know how many balls of each color went in. Okay. Okay. So, in this experiment, somebody will tell you there is an urn which has how many black balls? 1, 2, 3, 4, 5, 6, 7, 8. Okay. There is an urn with 8 black, and then how many blue? 4, 6, 9 blue, hopefully I am right, and then 8 red balls. Okay. So, this is like the starting point of the experiment. This is what describes the experiment. In fact, this 8, 9 and 8 is not really fixed. It can be changed. So, tomorrow you might have an urn with different colored balls of different numbers. Okay. So, whatever it is, you should be able to deal with it. Then somebody mixes up this urn and all the balls inside it a lot, and then probably closes their eyes and puts their hand inside the urn and picks out a ball. Okay. So, this is an interesting experiment, and what is the outcome? The color of the ball that you drew. Okay. So, that is the outcome. Okay. Outcome could be black or blue or red. Is that okay? The color of the ball that you picked from this urn is your outcome. Okay. So, this is an experiment that will be interesting, and you will see there are a lot of nice questions one can ask based on this experiment. Okay. So, the final experiment we will see is throw balls into bins. Okay. So, in this experiment we have a few bins, let us say we have 5 bins. Okay, so, this is bin 1, 2, bin 2, bin 3, bin 4, bin 5. Okay. And somebody is going to start throwing balls into these bins. Okay. So, he is going to close his eyes and throw a ball randomly. Okay. So, you have to imagine that this ball could land in any one of these 5 bins. Okay. So, that is so where it lands is the outcome you are interested in. Okay. So, you are throwing a ball in some sense in some way, in some crazy way from maybe a far distance or something, and then you can't really control, you do not know exactly which bin it is going to fall into, it could fall into any one of these bins. Okay. So, that is the experiment, and the outcome is just the number of the bin into which the ball fell. Okay. So, outcome is one of 5 possibilities, you are throwing one ball into the bin, okay, and it could be any one of these 5 possibilities. Now, what makes these experiments interesting? So, I am going to show you the previous experiment also. Okay. So, this experiment, all these experiments are already interesting, I am sure you will agree with me, but what makes them even more interesting to do computations with is that you can repeat these experiments multiple times, and you can start accumulating these results and then ask really very nice questions in probability and computing probabilities under such models. So, for instance, you could toss the coin twice. Okay. So, what happens when you toss the coin twice? Maybe I should show that in the next page. Okay. So, multiple repetitions of experiments result in more complicated probability spaces, more complicated outcomes. So, this is at the heart of probability. A lot of experiments are repeated and you have bigger and bigger sets of outcomes, and you have to be able to smartly do computations with these outcomes. So, if you look at first, toss a coin, let us say 5 times, okay, just to make it a little bit more interesting. So, we know that the outcome of one toss, I will denote it in shorthand now, you will see these shorthand notations are quite useful, h comma t, okay, heads or tails, right. The outcome of one toss is that. What will happen when you toss 5 times? So, you will have a sequence of 5 observations, okay, and you could have, for instance, heads, 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 or you could have tails, 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 or you could have anything in the middle. Okay. How many such possible things are there? Let us do some simple counting. Every toss is one of 2 possibilities, it could be either h or t. First toss could be 2 possibilities, second toss could be another 2 possibilities, third toss could be another 2, fourth toss is another 2, fifth toss is another 2. To find the total number of possibilities, you have to multiply all these possibilities together, 2 into 2 into 2 into 2 into 2, 2 power 5 possibilities, that is already 32 outcomes. Okay. So, if I want to write down the outcomes of all these tosses, I will have to have a much larger set. I will start with h, 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 then maybe h, 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 t, then maybe h, 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 t, h, then maybe h, 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 t, I am sorry, t, t, okay. And then you will have h, h, t, h, h, then h, h, t, h, t, and so on. Okay. So, I am not going to write every single possible outcome, I will close with the last outcome, which is t, 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 t. So, how many such outcomes are there? 32 outcomes. If you do not believe me, write down all of those things and check. Like I said, it is easy to count these things, and this is 32. Okay. So, now let us generalize a little bit. Let us say I toss a coin n times. Okay. So, what is this n? This n is some number. Okay. It could be 5, it could be 50, it could be 5,000, whatever. Okay. Whatever the number is, that is n. Okay. How many possible outcomes are there? There are 2 power n possible outcomes. Why is that? Because each toss has one of two possibilities, head or tails, and you repeat it n times. It's 2 into 2 into 2 into 2 into 2, 2 power n possible outcomes. And I cannot possibly list out everything, right? So n is already a variable, so I'll have to say it will start something like h n times dot 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 dot. I can't possibly write it down if n is big, it will go all the way to t t t t t. Okay, that's how the outcomes will look. Okay, so that's tossing a coin multiple times, n times. You will have so many different possible outcomes. Now the same thing you can do for the other experiments. Okay, so I'm going to not write down for all the other experiments in some detail. Maybe we'll see it later on. But if you can imagine, the same thing will happen with throwing a die. Suppose I throw the die twice. Okay, I throw it once. I have one of 6 possibilities. Second time I throw it, I make another observation of one of 6 possibilities. So how many total outcomes are there? 36 possible outcomes. 6 into 6. Okay, how do I write down the outcomes? What you saw in the first toss, comma maybe what you saw in the second toss. Maybe say 1 comma 3, 1 comma 4, 4 comma 2, 6 comma 6, 6 comma 1. Any one of those are possibilities if you toss the coin twice. Now suppose if I keep on tossing the coin and I'm sorry, I'm getting mixed up with the toss of the coin. So supposing if I keep on throwing the die repeatedly n times, then I will have 6 power n possible outcomes. Okay, how do I write down the possibilities? I will have a vector of length n. So maybe I should write that down for you. Let's say you throw a die n times, okay, and the outcomes, there are 6 power n possibilities, and they can be captured in a vector. Okay, so I could write it as something like, you know, d1 comma d2 comma dn, where di is either 1 or 2 or 3 or 4 or 5 or 6, right, is the outcome of the ith throw. Okay, so it's a very convenient way to represent in an abstract sense what is the possibilities when you throw a die n times. Okay, so let's also look at the other experiments we have. So they are also quite interesting. The third experiment we looked at was drawing a card from a pack. Okay, so now so far you had just one die and you kept on throwing, or one coin you kept on tossing. Now what happens when you draw a card from a pack? Okay, you've already taken one card out. Now when you want to draw another card, one important question is, do you put that original card back or do you not? Okay, so in these experiments, when you are drawing things from a pack or drawing balls from an urn, you have to ask this question: are you going to repeat the experiment with replacement or without replacement? Now that is very critical, because the number of possible outcomes changes a lot, whether or not you are doing with replacement or without replacement. Okay, so let's think of the cards. Supposing in the first draw I drew the ace of spades. Now if I am drawing without replacement, without putting it back, I am drawing one more card, there is no chance I will get ace of spades again, because ace of spades is gone from the pack. Okay, so I have only one of 51 possibilities in the second draw. On the other hand, if I put my card back, the card that I drew back, then mix it up again and draw, I can get ace of spades again. Okay, so the outcomes and the nature of the outcomes differ based on how you do the experiment. So when somebody describes the experiment to you, you have to pay a lot of attention and understand exactly what that experiment is. So when they are drawing a card, are they drawing it with replacement or without replacement? Okay, so that's critical when it comes to repeating drawing of cards. The same thing holds for drawing a ball from an urn. Okay, so things change depending on whether or not you put the ball back when you repeat the experiment. Okay, so that's also critical. The same, if you look at throwing balls into bins, it's not really too critical. I mean, there's no question of removing the ball from the bin or anything. You could just keep on throwing multiple balls into the bins and finally observe how many balls landed where, first ball landed where, second ball landed where, etc., etc., etc. All those things you can observe. Okay, so there are some variations here, but these variations you have to pay attention to. Okay, so let me maybe describe this cards example, or maybe the drawing the ball from an urn example I will do with replacement and without replacement. Okay, so maybe a smaller example. So, third one, from an urn with replacement. So, this is going to be my third example. So, I have an urn with, let us say, 4 black and 5 red balls. Okay, just 2 colors this time, not 3 like the previous example, and I am going to draw 3 balls with replacement. Okay, what are the possible outcomes? How many possible outcomes are there? In the first draw, I can have 2 possibilities, it could be either black or red. In the second draw, again 2 possibilities, black or red. Third draw also there are 2 possibilities, black and red. Okay. So, in fact, you can keep on repeating it. If you have n different draws, again every draw you will have black and red, because you are doing it with replacement. Okay. So, the outcomes are going to be black, 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 red. There are 8 outcomes. They are small enough, so I can write it down: black, red, black, black, red, 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 black, black, red, black, red, 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 black, and red, red, red. Okay, so it's easy to write down. So in fact, if you were to draw n balls, you will have 2 power n possible outcomes, as long as you are doing it with replacement. Now, what happens if I draw? So this is maybe part A. Part B is draw without replacement. By the way, I should point out the word draw has multiple meanings in English. It is not just drawing a diagram. Draw also means you are pulling something out. Okay. So, draw without replacement. Okay. So, if you draw without replacement, some interesting things will happen. Okay. So, for instance, so let me take the first case is you are drawing 3 balls. So, once again you have 4 black and 5 red. Let us say you are drawing 3 balls. Okay. If you are going to be drawing 3 balls, what kind of outcomes are possible? Okay. In fact, all of the 8 outcomes are possible, right. You can have black, black, black all the way to red, 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 8, all 8 possible. Supposing I were to draw, let us say 5 balls. Okay. So, I am drawing them without replacement. So, the ball I pick out, I am not going to put back. Okay. Now, can you have 32 different possibilities? All the 32? Actually, no, you will only have 31 possibilities. Why is that? Okay. Because there are only 4 black balls. If you took 4 black balls in a row in the first 4 draws, the next draw will definitely only give you a red ball. It cannot give you a black ball, because black all 4 you have taken. Okay. So, B, 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 5 Bs will not be there. The first possibility will be B, 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 R. Okay. And after that, all possibilities are possible. You can go all the way to R, 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 R. Okay. So, now the situation will become more and more confusing if you consider a larger number of draws. So, let us say, okay, I think I am making a bit of a mess here. So, this is the second possibility, this is the third possibility. Okay. Let us say I draw 7 balls. Okay. So, this is going to be a bit interesting to think about. How many possible outcomes are there? Okay. So, I will leave it as an exercise to you. You have to think about what is possible. If you are going to draw 7 balls, all 7 cannot be black, all 7 cannot be red. You will have a certain number of black, a certain number of red occurring in some order, so that the total comes to 7, and you can have at most 4 black balls and at most 5 black balls. Okay. It is an interesting counting problem. Okay. So, that is what I meant when I said, when you start repeating things, repeating experiments, simple questions like number of outcomes become quite a bit confusing, right? You'll have to do a lot of careful calculation to come up with the numbers. Okay, so this is going to be an assignment for you in some form. Maybe we will ask a question on it in the assignments this week, and you can try and work out an answer for it. Okay, so as the number increases, you can tell me, you can be sure that it's going to become more and more complicated to figure out the possibilities that can occur. Okay, so another interesting case you might want to consider is supposing we draw 9 balls. How many outcomes are there? Okay, so these are interesting questions for you to think about. Just the number of outcomes. You don't have to list out every possibility. What will be the number of outcomes? This is an interesting question. Okay, same thing happens in the pack of cards. The pack of cards is even more complex. There are so many different possibilities. If you draw with replacement, without replacement, you'll have to think of all the different cases that can happen. And I'll also give you the last example that I'll do in this lecture is about throwing balls into bins. Let's say we throw, this is what is the number here? This is the 4th one. Let's say we throw 10 balls into 5 bins. Okay, so we had the 5 bins before. Previously I was just looking at 1 ball going into a bin. Now I'm going to draw 10 balls into 5 bins. 5 bins. Okay, I'm throwing 10 balls. Okay, now a lot of things depend on whether or not you think of the balls as indistinguishable or distinguishable. Right, you have 10 balls. Do you think of them as, say, ball 1, ball 2, ball 3? Maybe you have numbered each of the balls so that after they go into the bins, you know which ball came first, which ball came second, which ball came 7th, etc. Or you may not bother with those numbering. You might have just all balls the same. You just throw it into it. You only care about how many balls went into which bin. Okay, so both situations are interesting, whether the balls are distinguishable or they are not distinguishable. Okay, so let me consider the first case where balls are distinguishable. Okay, what do I mean by distinguishable? You can tell one ball from the other. So, for instance, maybe balls are numbered 1 to 10. Okay, you had 10 balls like that. So, in this case, it's interesting to maybe put down the outcomes in this form, in this probably simple form. You can write B1, B2, B3, B4, B5, B6, B7, B8, B9, B10. And what are these BIs? Each BI is the bin number into which the ith ball landed. Okay. So, this is a convenient way to group all outcomes when you can distinguish the balls. You put a vector of how many ever balls you had and then write down which bin it went into. Okay, and then you can start answering questions. So, if you were to look at this question, so there are 10 possible values in this vector. Each BI can be one of 5 possibilities, right? Each ball can go into any one of the 5 things. So, you will have 5 to the power of 10 possible outcomes. Okay. So, there is also the other case where balls are indistinguishable. Okay. So, maybe these are all similar tennis balls and you are just worried about how many balls went into each bin. Okay. So, here if you throw 10 balls, the outcomes, it is interesting to capture them, let us say as N1, N2, N3, N4, N5, and what is Ni? Number of balls in bin I. Okay, hopefully this is clear to you. I have thrown 10 balls, they are all indistinguishable, same balls, and at the end, and outcome I am interested in is how many balls ended up in each bin. Okay, Ni is the number of balls in bin I. Okay, so now here again is this interesting little count that we have to do. So, how many different possibilities are there for this guy? Okay, supposing you did 10 different balls. So, N1 could be 0, n1 could be 1 or all the way up to 10. All the 10 balls could have fallen into the first bin. Okay, n1 can take one of 11 possibilities. Same thing is true for n2. n2 can take one of 11 possibilities. Maybe none of the balls fell there, maybe all the 10 balls fell there. Everything is possible. But you cannot have the case that n1 is 10 and n2 is also 10. Why? Because there were only 10 balls to start with. Okay. So, you have this constraint that each ni is between 0 and 10. Okay. Each ni is between 0 and 10. Of course, ni is an integer, it is not anything else. And what is the other constraint? n1 plus n2 plus n3 plus n4 plus n5 should be equal to 10. So, each of these numbers are not independent. Like in the previous case, when the balls were distinguishable, each of the BIs could be go to any one of the 5 bins. We did not really bother about any constraints there, but here when you are worried about the number of balls in each bin, this kind of confusion comes. So, the number of cases is not immediately obvious. Okay. So, once again this will be a question for you to think about, how many different possible outcomes are there. Okay. So, now I can generalize this 10 and 5 are not in any way so interesting. You can say m balls into n bins. Okay. So, you could generalize this as m balls and this is n bins. You can imagine the calculation is going to become even more complicated. It turns out there is a very simple trick to compute the number of outcomes here, which some of you might have learned. Maybe it is new for some others, but it is possible. So, hopefully I have convinced you that these simple experiments that we had, at some level they are simple experiments. Okay, tossing a coin, throwing a die, drawing a card from a pack, drawing a ball from an urn and throwing balls into bins. These, when repeated multiple times under different options, can become quite a bit complicated sometimes, but they are also really interesting. So, this is what makes a foundational course in probability very important. When you learn the tricks to find to deal with these kind of examples nicely, any other application that you see involving more sophisticated concepts in probability also become interesting. So, this is the starting point. I hope you have a good time for the rest of the course, and this is just the first week. We are only getting started and things will get much more interesting than this as we go along. Thank you very much.